Let us examine the Gram-Schmidt process. We will begin with the simpler problem where the columns of X are independent. And hence, because they are independent, we call it a basis. And this set of P vectors spans a subspace W for Rn. What it means is that each of these is dimension n, and we have P of them. For it to be a proper subspace, P is less than, for example, in this case, n. The Gram-Schmidt process basically is going to take from this set of vectors to produce another set of vectors, the same number of them, P of them. But in this case, the relationship of V to his other counterparts, Vi dot product with Vj is equals to 0. That means we are producing a set of orthogonal vectors. Because there are P of them, we call it the orthogonal basis. Because there are no extra columns. The columns of V's are independent columns, as in the set of the x1 to x2 to xp. The important point is that V1 to Vp or V1 to Vk in this will span the same space as x1 to xk. How do we do this? If, for example, if x only has one vector and we are only allowed to extract one vector, then the simplest thing to do is to say that V1 is equals to x1. Therefore, V1 spans the same space of x1. So this is obvious. What happens if now we have two vectors? We have x1 and x2. That's all. If we have already used up x1 by V1, what about V2? Remember the orthogonal projection idea. The second idea is that the second V2 should be orthogonal to V1. And how do we do that? We use this equation. To understand this equation, let's draw a pictorial representation in R2 space. Let us think of this as x1, and let us think of this as x2. We have already chosen V1. V1 is the same as x1. We are going to project x2 onto V1. How do we do that? The projection of x2 on V1 is here. This little guy here, x2 projecting onto V1, is the closest point along V1 to x2. What is this vector that I'm drawing now in purple? This vector is nothing but x2 dotting with V1 divided by V1 dot multiplied by V1. So it is a line. It is a line along V1, and it has a scale of, it is scaled by this value. And this scale of this value will bring it to a point along V1 that is closest to x2. Now, if this is the closest point to x2, this is the residual, and we would let this residual be V2. So V2 is equals to x2 minus the projection of x2 on V1. The projection of x2 on V1. And this term is here, and we get the second equation. Let us now try to get the third equation, V3. V3 is equals to x3 minus the projection of x3 on V1 minus the projection of x3 on V2. We are taking away the contribution by V1 and V2, leaving up with us whatever left is called V3. Let us also see this graphically. This is x3, and we have already chosen V1, and we have already chosen V2. This is right angle. V1 is orthogonal to V2. V1 and V2 spans the first two columns of W, which is x1 and x2. This is what it's trying to say. When we want to find x3 onto W2, that means that from the first two columns, on the space of the first two columns of W, this is the point. This point is the closest point in the W space to x3. No other point is closer than that. This is called the projection of x3 onto W2, and the equation for this is here. So we can say that the projection of x3 onto W2 is equals to x3 dot with V1, V1 dot with V1, V1 plus x3 dot with V2, V2 dot V2, V2. The whole thing is actually x3 minus this guy to produce V3. The interpretation is actually more important. The calculation looks a little bit scary, but the interpretation is much easier. It basically says that to calculate the third V3, so you see, to calculate the third V3, we take x3, we minus this guy to get, so hence it is this vector plus V3 is equals to x3. That's the idea. But how to find this vector closest to x3 in the space of the first two columns, or in the space of W2 in this example, is this equation called projection of x3 onto W2. What is projection of x3 onto W2? It is nothing but these two guys adding up. Okay, now we can then continue up to VP. The interesting thing is that the V's found by this will form the orthogonal basis, because you realize that we are always taking the orthogonal parts, that is left after using the other vectors. The next slide I took from Lay, which gives the detailed proof of this, but we will not go through it here. You can read. And now we follow by an example.